All right, so let's continue on with problem number 9. We have another problem where we need to simply substitute in the values for x and y into our equation. It says find the value of the expression if x squared equals 2 and y squared equals -4, and we have x times y all raised to the second power. So we go ahead and plug in 2 for x, we plug in -4 for y, and we see that there's multiplication going on in here. So first we multiply what's on the inside of the parentheses. We end up with -8 raised to the second power, which is 64, and we're moving on. Number 10 says find the value of the expression if x equals 5. So we have the square root of x squared, and we're going to plug in 5 for x. So the square root of x squared then becomes the square root of 5 squared, which in turn becomes the square root of 25, 5 raised to the second power is 25, and the square root of that is 5, and we're moving on. Number 11, another substitution problem. We plug in 3 for x, -7 for y. We get x squared plus y squared is going to equal 3 squared plus -7 squared. Notice that when you plug it in, if you are using your calculator, be mindful of your parentheses here. You have to put this -7 in parentheses, otherwise it might return you the incorrect answer or even an error. So we have -7 squared, which is going to be 49. So we have 9 plus 49, which equals the square root of 58. Notice that it says simplify your answer and type an exact answer. So we're not going to simplify the square root of 58 and type in the decimal. Here we're going to actually put the square root of 58 as our final answer. Okay, next one, number 12, another substitution problem. We have x raised to the y, and we're plugging in x equals 3 and y equals -3. So we plug in 3 for x, which is our base. We plug in -3 for y, which is our exponent. We end up with 3 raised to the -3rd power. Once again, negative exponent, we change its position in the fraction. Now it's down here in the denominator, and we can simplify 3 to the 3rd power, which is 27. Number 13 says 4 raised to the 3rd power. We also have 27 raised to the 2/3 power, and we have 2 raised to the -2nd power. So let's look at it. 4 raised to the 3rd power is simple enough. We get 64, and that is the final answer for that one. 27 raised to the 2/3 power is a little bit trickier, so now we have to go back and remember our rules for how we separate or how we rewrite an exponential expression when we have a fraction as our exponent. So remember, the denominator of your rational exponent is going to end up being the index when we write it as a radical expression, and the numerator will remain as the exponent. So the 2 is the exponent, the 3 becomes the index. Denominator, index, numerator, exponent. So now we have the cube root of 27 squared. Notice that in this next step, we've moved our 2 to the outside of the parentheses. This simply indicates that we're going to take the cube root of 27 first before we actually square our final answer, because that will break it down before we make the expression bigger. 27 squared will be something large. We still end up with the same answer, but it's a lot easier to square 3 than it is to take the cube root of whatever 27 squared is. Of course, if you're using your calculator, it doesn't really make a difference. So we end up with the cube root of 27 being 3. 3 squared is 9. 9 is your final answer, and you're moving on from there. The final one, we have 2 raised to the -2nd power. 2 raised to the -2nd power, again, negative exponent changes position in a fraction. We have 1 over 2 squared, and 2 squared is 4, and we're moving on. Okay, so next we're going to look at 14, 15, and 16. They're all asking about the same thing. They're just asking about the graph of the exponential function f of x equals a raised to the x, where a can be any number that is greater than 0 as long as it is not 1. So the base of your exponential function has to be positive, and it cannot be 1. So whenever you have an exponential function that's written that way, the graph will always look like this. It's always going to pass through the y-axis. It's always going to have the y-intercept at 1, and the x-axis is going to be a horizontal asymptote. Always, whenever you have something raised to the x power with no transformations, you are going to get this picture. So these questions are asking essentially about what this picture is looking like. So it says the domain of the exponential function is the set of all real numbers. So if we look at the graph, we see it goes from negative infinity to positive infinity. It is indeed all real numbers. So 14 is going to end up being true. Number 15 says the graph of the exponential function has no x-intercept. If we look at it, once again, we said the x-axis is a horizontal asymptote, so it is not going to cross the x-axis, so indeed it will not have an x-intercept. So this one is also going to be true. And notice that they sometimes switch up the order of the false and true questions, so make sure that you click on the correct answer when you're working on your assignments. Number 16 says, which of the following is the range of the exponential function? Again, the range is from the lowest point of the graph going up to the highest point. The lowest the graph goes, well, it approaches 0, but it never touches it. There's your bell. It approaches 0, and then it goes up to positive infinity. So the range is going to be from 0 with a parenthesis, 0 not being included, to positive infinity. If you wrote it as an inequality, it would be y is greater than 0. So we would click from 0 to positive infinity, and it would be this answer choice for number 16. Now, number 17, and I think a couple of the questions after it. So they present you with a table of information, and you need to determine whether or not the function is going to be linear, exponential, or neither. If the function is linear, you need to find a linear function that models the data. If it's exponential, it says find an exponential function that models the data. So now, when you're looking at the information and it's given to you in the table, let's look at some examples that we have over here. So in order for it to be a linear function, first and foremost, you want to make sure that the x's are increasing at a constant rate. In all of our examples that we have to cover, they will be, but you still just want to be mindful of that before you start checking your y's. So when you look at the y coordinates over here on the right side, if it is linear, it will be changing at a constant rate. Basically, it'll be adding the same number or subtracting the same number for each successive y coordinate. So if you look at this linear function going from 5 to 2, okay, you say, okay, it subtracted 3. So now for all of the rest of the y coordinates that come next, it should be a difference of 3. So 2 minus 3 is negative 1. Negative 1 minus 3 is negative 4. Negative 4 minus 3 is negative 7. You also could have gone in the opposite direction if you prefer. Okay, to get from negative 7 to negative 4, I have to add 3. So plus 3, that gives you negative 4. Plus 3 gives you negative 1. Plus 3 gives you 2. Plus 3 gives you 5. It's safe to say that this will model a linear function. It has a constant rate of change, which is 3. Looking at the exponential function over here on the right side now. In this case, you want to make sure that it's either multiplying by or dividing the same number for each successive term. So 32 divided by 2 gives me 16. 16 divided by 2 gives me 8. 8 divided by 2 gives me 4. 4 divided by 2 gives me 2. So it's not always as obvious, so sometimes you can't just look at it and say, okay, I know what number is dividing by. So in this case, you look at the lowest number and then you just check to see what the ratio is between the two numbers that will be next to each other. So what I mean by that, we would do 2 divided by 4, that would give you 1/2. 4 divided by 8 would also give you 1/2. 8 divided by 16 is 1/2. 16 divided by 32 is 1/2. So we have a common ratio of 1/2 because the ratio between each term is 1/2. Also, because you have a common ratio, that tells you that it is going to be an exponential function. And if it doesn't have a constant rate of change or a common ratio, then it is neither exponential or a linear function. So we see, okay, going from 2 to 4, it increased by 2. And then we say, okay, did it increase by 2 again to get to 7? No, it increased by 3. So it doesn't have a constant rate of change. Now if we look for a common ratio, we could say 16 over 11 will be the first ratio, but then you have 11 over 7, which doesn't reduce. You have 7 over 4, which also doesn't reduce. So it's not a common ratio going on here, and it is not a constant rate of change, so it is neither exponential or linear. So now let's go back to number 17. So we have our table here, and we want to see, okay, does it have a common ratio? Does it have a constant rate of change? Obviously, it doesn't have a constant rate of change. To go from 112 to 1, you have to add some fraction. To go from 1 to 12, you have to add 11. And then to go from 12 to 144, you have to add a whole lot more. However, when you divide the terms, when you do 1728 divided by 144, you see that you get 12. When you divide 144 by 12 again, you get 12. When you do 12 divided by 1, you see you also get 12. Therefore, it's safe to conclude that the common ratio is 12, and our base for our exponential function is going to be 12. Now, we need to make sure that there are no transformations on the exponential function. So again, if we go back to that original graph of our exponential functions like we talked about earlier, it should always have the point 0 and 1, and then the first point on your exponential function graph is going to be 1 comma whatever the base is. That means if you have those points, then it is going to be an exponential function with no transformations. If you have something different, it is going to be a different scenario, and we'll talk about those when we get to them. So now, if you start out with 12 to the x, you just check, okay, when I plug in 0, do I get 1? The table already indicates that you get 0 and 1. And when you plug in 1 into the function, you get 12. Also, if you plug it in down here, 12 raised to the 0 power is 1. 12 raised to the first power is 12. So we know that these points are going to be on this graph, and that matches this table. So it is an exponential function. So we would click B. The exponential function that models the data is going to be f of x equals 12 raised to the x power. And then we are moving on to number 18. Number 18, it's looking like it is probably going to be another exponential function. Of course, we want to go ahead and check just to make sure. You can take the number divided by the previous term, the previous y value, and we see we get a ratio of 11, and then you continue to divide to make sure that the ratio between your terms are all 11. So it's safe to conclude our common ratio is 11. However, for the first term, we have 0, 12. We don't have 0, 1, so it must be some type of transformation. So here's how you check to see what the transformation of the function is. You start out with f of x equals a times 11 raised to the x power. So first we're looking for what a is to see, okay, is the function being multiplied by something. Then you want to take any point in the table. You want to take any x and matching y value and then plug it in for x into this setup that you have here. So you're going to write out f of x equals a times your base, in this case is 11, or your common ratio, which is 11 raised to the x power, and you're going to plug in a number for x, and then you are going to solve the equation for a. So when you have f of 2, you're plugging in 2 for x, that should equal 1452. So f of 2 equals 1452, and that equals a times 11, with 2 plugged in for x here.